Today's webinar. We'll be running a live Q&A at the end of the webinar, so if you have any questions, please feel free during the webinar to go ahead and add your questions in the chat, and we will answer them after the webinar. And if you miss anything, we'll be sending a recording of the webinar when it's available. So I'm Dr. Janet Six, Senior Product Manager at Tom Sawyer Software, and today we're going to be talking about unlocking the potential of big data with graph analysis. And we're going to show several examples with Tom Sawyer Perspectives. So first of all, let's talk briefly about what Perspectives is. Tom Sawyer Perspectives is an SDK and low-code graph visualization and analysis development platform with integrated design and preview interfaces and extensive API libraries that allow developers to quickly create custom applications that intuitively solve big data problems. So how does Perspectives do this? So first of all, Perspectives can federate data across many different sources into a single native graph model. These data sources can include graph databases such as Neo4j and Amazon Neptune, Azure Cosmos, and Janus Graph. And in addition, Perspectives also supports relational data sources such as SQL or Postgres, and JSON, XML, or RESTful data sources as well. And so once the data is brought together into the single graph model, then the data can be processed and transformed. And then we can create interactive applications with views of several different types for the data and is tailored for a specific use case. So in today's webinar, we're going to be specifically discussing graph analysis. And we're going to be discussing techniques that explore real-world use cases that can benefit from graph analysis. We'll also discuss how to integrate graph analysis techniques with big data so that we can uncover deeper insights. And we'll also discuss key benefits of graph analysis in deepening data comprehension, driving operational efficiency, facilitating innovation, and enhancing decision making. So as the first part of that, we will take a brief overview of what a graph analysis is and how it can be useful. So first of all, what is graph analysis? Graph analysis is the application of data-driven techniques for the discovery of actionable information. And there's many different types of graph analysis, and we have some broad categories here. We're going to take a deeper look at these in a few moments. So graph analysis can help you to discover areas of interest in data, optimize complex systems or processes, and deliver key information to stakeholders and decision makers in a timely manner. There are many benefits of graph analysis, and I won't say everything that you see here on the screen. For example, you can analyze complex systems models. You can find key people in social networks. You can do optimization, look for patterns. You can even use analysis to understand future scenarios as well. And so these graph analysis algorithms can be run in real time or through automated background processes or interactively by users, as we'll see here in a few minutes. The importance of graph technology is being understood more and more. And as you can see here with this quote from Gartner, Gartner predicts that by 2025, graph technologies will be used in 80% of data and analytics innovations, up from 10% in 2021, facilitating rapid decision-making across the organization. Tom Sawyer Perspectives has a very powerful combination of graph analysis with graph visualization. So as we see here, we have applied graph analysis to a system, and the combination of knowing the key elements in this system with the visualization, which show us where these important elements are and how they're related to other elements in the system help us to get information not only more quickly, but more effectively as well. So let's talk a little bit more about the graph analysis that's available in Tom Sawyer Perspectives. And we have several categories of graph analysis algorithms, as we were talking about earlier. So let's take a closer look at these large categories of algorithms. So first of all, we have traversal analysis algorithms. And these enable you to understand how to best visit all the nodes of your graph in an effective order. And perspectives includes these three algorithms. Partitioning algorithms determine how to best divide a graph into pieces to help you discover natural groupings in your data. And perspectives include several of these algorithms as well. Clustering algorithms identify areas with higher connectivity by finding different types of natural clusters or groups in the topology of your graph. And so we have several techniques. We're going to be using clustering here in a few minutes. Pathfinding algorithms help you discover important paths within a graph to show the most efficient or most important ways to get from one graph element to another. There's many types of path analysis techniques, and we'll be using a few of these here today as well. Cycle analysis algorithms find cycles and circular dependencies in graphs. And there are several of these techniques in perspectives as well. Tree analysis can determine effective tree structures within a larger graph. Then there are social network analysis algorithms, which give each node a ranking based on importance factors. And perspectives includes several of the top known centrality techniques, and we'll see how some of these work here soon. Network flow algorithms can determine flows through a system with a high output or of low cost, as well as find vulnerabilities in the system. So as you can see here, there are many different types of algorithms. And so you not only need to know which algorithms exist, you also need to understand which ones are most effective for your use case. And sometimes for your use case, you might need something that is custom, something that works specifically with your data and the types of results that you need. So at Tom Sawyer Software, we have many people on staff who have been in the graph field for decades. So we can help you to design and implement an effective and efficient technique for you. So now we're going to look at some specific examples of using graph analysis for different use cases. So first we're going to start with our crime network example. And in this example, we are going to show how to apply several types of analyses in sequence. So path and social network analysis in this example. So let's take a closer look at this data. We are looking at a crime network, and let me zoom in to part of it. And what we have here is the original data, which is showing us criminals and the crimes that they have committed. Sometimes the original data is not the data that we want to analyze. So in this case, we have, and let's zoom in just here a little bit further, we have two criminals that have committed two thefts together. But let's say that we want to understand more about the social network and who are the key people in our crime rings and who's working with each other. So this data is not exactly the data that we want to analyze. What we want is we want to understand the connection between these two people because they have been committing crimes together. So what we do here in this application is we take the original data here and we compute a new graph. This is the people network. So now we look directly at the criminals that are working together and doing crimes together. So let's zoom in here. And we have found that two people here and here are of particular interest. We have found this in our investigation. So we want to focus in on this part of the crime network and understand the part of the larger network that is related to these two criminals. So we are going to perform a reachability analysis. We select these two criminals and we set them as a hop start, which means that we are going to make them focal people in this portion of the network. And then we're going to perform a reachability analysis so we can work with just the piece of the crime network that we need right now. We need to zoom in and find out what's going on with these criminals and the network around them. So we have zoomed in, we've reduced the size of the graph that we're working with. And now we're going to run a second analysis. We're going to run a centrality analysis. So we have several types of centrality analysis, as we mentioned here a few minutes ago. And right now we're going to run a betweenness centrality analysis. And so betweenness centrality is going to help us determine which people in the network are on the superhighway of information or in the most activity in the network. And so we can see that these two people here are on pathways of communication in our social network. But maybe that's not the information that we are looking for today. Maybe we want to know who is the most highly connected in this network, who has the most direct connections. So we're going to perform a degree centrality. And now we can clearly see who are the people in the network with the most direct connections, where they're located, and how they're located to each other. So in review of this example, we visualized the original data, then we computed a graph that was needed to answer our question. Who are the key criminals that are working together? Then we performed a reachability analysis to focus on the key part of the criminal network, and then applied different types of centrality analysis to understand who the key players are in this portion of the crime network. Okay, so now we're going to go on to the next example. And I please, there's a few people out there unmuted. If you don't mind muting, please. We're getting a little bit of extra noise. Thank you. All right. Okay, so here is our second analysis example today. So this is a telecommunications network, and we are looking at several antennas and how they are connected to each other. And we have a couple of questions that we're going to answer today with this example. And we're going to be using path and cluster analysis. So first, we're going to do a shortest path analysis to understand how some specific elements in our system can have the fastest or the lower cost communication. So I'm going to select this element. I'm going to set it as the start node. And then I am going to select over here, set this as a finish node. And I want to know what is the shortest path between these elements. So I'm going to apply a shortest path analysis. And so now we clearly see that in our visualization. And so here's another one of the examples where it's really nice to have both graph analysis and the visualization so that we can see and communicate these key results. And as you can see, the visualization has focused in to the shortest path by changing the coloration of the way the edges are drawn as well. Okay, very good. So now we're going to apply a second type of analysis because we want to see a summarization of the graph at a high level, what's going on here. So we're going to apply a different type of analysis. We're going to apply a clustering analysis. So again, clustering are telling us that we have some natural groups within a graph given the topology or given how the nodes are connected to each other. So you can see here how the colors of our antennas has changed. So each color represents one of these natural groupings in the topology of the graph. And so, of course, this is very nice right here because we have not only the visualization, but we have that colorization of the nodes giving us high level information about the graph. But we can take it another step further. Let's go ahead and abstract these nodes or antennas that have the same color into their own nested drawing. So we're going to say group by cluster. I'm going to apply a new layout. And you can see here that we have a summarization over here, a high level view of what's going on in the backbone of this communication network. I have opened a couple of those clusters. Let's zoom in. And we still have the high level information here. You can see that all of the green antennas are inside a green parent node. We have all these red antennas inside a red parent node, but we have not lost the detail of how these antennas are connected to each other. We can still see all of the full connections between them. And if we want to see the most high level, we can do a collapse all as well. So in review of this example, we visualized a communication network using label and edge colors, which convey information about the network and the connection loads. We applied shortest path analysis between selected elements in the network. And then we applied a different type of analysis in order to see a summarization of the graph. We used clustering to find groups with higher connectivity in the network, and then we were able to abstract the clusters into nested drawings in order to see a summary of the network. Okay, very good. All right, so now let's go on to our next analysis example. In this one, we're going to be working with paths and map views. So in this example, we're going to show how to find some lower cost paths for logistics. So we have here on the left side a map view where we're going to study the shortest path between 2 points. And on the right side, we're going to show alternative paths because we might need that for logistics reasons. So first of all, let's go over here and use the shortest path first. I'm going to select the node here that represents Iceland, and we can bring up some additional details about this particular location. We have the name, for example, and the latitude and longitude information. We also can show information for these connections between the countries as well. So in this case, we can see the distance in kilometers between these two locations. Okay, so now we want to plan for some shipping between Iceland. So I'm going to set this as the start node and Slovakia. And I'm going to set this as the finish node. And now I'm going to apply a shortest path analysis so I can see the shortest distance path between these 2 points. And so we have that highlighted here in yellow. Now, sometimes we're not able to use the shortest path for various reasons. Maybe there's a road that's under construction, or there's some a bad winter storm, and we need to find an alternate route. But we want to find still a good low cost or low distance, in this case, route. So we can use the sorted path analysis to see alternatives. So I am going to, over here, apply the sorted path analysis. Now, these look the same, right? Well, that's what we expect because we are going to have many paths between these two different cities, and we want to sort them by distance. So, of course, we would expect that we would see the similar shortest path at the beginning. But let's say we already decide we can't take that. So show me what are other good options. So I can say, give me the next path. And you see how it changed slightly down here. So now we have an alternative, but still lower cost path. Let's say that we have a winter storm. We can't go this way, so that won't work. So we keep going to the next path until we see something that's different enough that we have worked through the storm. And down here at the bottom in our tree view, we can see the distance of the shortest path was 3,039 kilometers. And the length of this path that we just found was 3,161 kilometers. So we've been able to get around that winter storm, and we've added about 120 kilometers. So we still have a nice low-cost path. So in review of this example, we applied both shortest path and sorted path analyses in order to find multiple good alternatives for logistics planning. All right, so now we're going to go on to our next example where we're going to show how to maximize flow or throughput through a system. So we want to understand how we can get the most out of this system. And there are analysis techniques that can help us with this. So we're going to select station 1, and we're going to set that as our start node. And station 13, we're going to set this as our finish node. Now we're going to apply our maximum flow analysis, and we can see which parts of the system are used as this maximum flow. And the total flow, by the way, is 95. So we can get 95 units through this system. So this may be in a factory, and you're trying to push as many elements through the system as you can. And these are your different stations on your factory floor. And we can get an output of 95 through this part of the system. And notice that some of your connections are not being used. So you may be able to use this information to help optimize your system. Maybe you need to take some of these connections or some of these people here at station 9, for example, who are not being used at all, and maybe reassign them to a different task so you can get more work done in parallel. All right. Now, let's say that you don't want to study the whole system. You want to study just part of the system. So let's again look at station 1 as our start and station 8 as our finish. And again, we're going to apply maximum flow. And now we can understand how to maximize the flow in part of the system as well. Good. So in review of this example, we used a maximum flow technique in order to increase throughput in our system. All right. Okay, so now we're going to use this example to talk about how we can find vulnerabilities in a system. And we're going to be using a partition analysis here. And so let's say here that we have a communications network. And we want to understand, well, where is the system vulnerable? And, we're looking at our visualization, we can see, well, things look pretty well connected to each other. But, where is it that we might lose communications if we have problems in our system? Well, let's run this data-driven analysis and find out. So we're going to apply bi-connected components analysis. And you'll see how some of these elements turn red. Okay, so what does that mean? These red nodes are called articulation nodes. And if we remove any of these from our system, then parts of the system will become disconnected. So if we're looking at a communications network or a computer network or a social network, and we lose some of these red elements, then we will have parts of the system that cannot communicate with the rest of the system. So these red points are vulnerabilities. And so now that we have that information, we could take several points of action. So for example, we could put a higher reliability element at these locations that are in red because we know that it is especially crucial that these elements don't go down. Or we might decide to add to our system. Maybe we need to add some more nodes or more connections between this part of the system so that these would be no longer articulation points. So in summary of this example, we use partition analysis in order to understand vulnerabilities in our system. Okay. So far today, we've used several different types of analysis, and these are all available in Tom Sawyer Perspectives. But let's take a moment to talk about, well, how do you add analysis to an application with Tom Sawyer Perspectives? So we're going to open this example in Perspectives Designer. So here is that low-code development platform that we discussed at the very beginning of the webinar, and here we have the definition of the application. We can see the schema, as well as the data sources we're integrating with, our drawing templates, or how do the visualizations appear? Which shapes are the nodes? What color are they? Are we using images or a composite UI? That's defined here. Then we have our graphs and analyzers, which are used for analysis. We'll come back to that in a moment. And then here's where we've defined our data visualization views. And then we can define things like filters and search, which can be applied to several types of views, and in our view layout, which is where we create our dashboard as well. But for the moment, we're going to focus in on analysis, and let's add another analysis. So the graph and the analyzers here work together. Oh, well, what's the graph? Okay, so let's step back here for a moment. We have our schema and our data integrators so that we can bring data from our database into the Tom Sawyer native graph model. And that model can be very large. And sometimes we do not want to run analysis on the entire graph. We only want to do on part of the graph. And that's what this graph is. This will be what we are performing the analysis on. And then we have the analyzer. And you can see here's that by connected components analyzer that we were just using in the previous example. So let's add a new type of analysis. So I'm going to click Analyzer, right click, Add Analyzer, and we're going to use a clustering analysis. So I'm going to type in clustering, and then here's the point where we select which type of analysis that we want to use. And you can see here there's many types of analysis. Right now we're going to pick clustering though. And then again, it's saying what graph do you want to work with? Well, we're going to use the same graph that we used for our bi-connected component analysis. So I click OK, and now we're going to define this analyzer a little bit more. So we are going to go to our model rule, and I'm going to add an action to set a graph option. So many of these analysis techniques have different parameters that you can set that affect exactly how the analysis is applied. And so in this case, I want the clustering to have a different balance. Well, what's balance? So if I click on this here, the designer is going to bring up some information. What is it that we're doing? What is balance about? Well, it tells us here. Balance is about creating similar sized clusters or not. And I do want to have clusters that are pretty similarly sized. So it tells us here that larger size numbers favor creating similar size clusters. So I am going to change this 1 to a 4, and I'm going to click OK. And then I'm going to click OK again, and I'll take the rest of the default attributes for our analysis. And then I'm going to come over here to Preferences, and I'm going to ask to create a drawing view in the preview, meaning that I want to see a preview of what these analysis results would look like. Okay, good. Now let's go back to our web preview and see how this clustering looks. Okay, so I've opened the web previewer. Here's that example that we were just working with. There's our articulation nodes, but what about the clustering? What would those results look like? So let's go over to our clustering preview, and now we can see this graph with the clustering applied. And so the nodes of the same color are going to be the ones that are in the same cluster. So in review this example, we applied clustering to a existing application, and then we saw the results in the web previewer. So several of these examples that we looked at today are available on our graph application examples page on the tomsawyer.com website. And all of the examples are available in Perspectives, and you can use those either as a customer or you can reach out to us for an evaluation. So we appreciate you joining us today. And we discussed, first of all, an overview of graph analysis. Then we went through several examples of using graph analysis to solve big data problems. Specifically today, we used reachability, social network analysis, clustering, shortest paths, sorted paths, maximum flow, and bi-connected components analyses. And then we also added analysis to an existing Perspectives application. So you can read more about graph analysis at our website, and we have additional videos about analysis and other topics as well on our YouTube channel. So please contact us today at tomsawyer.com to start your free trial of Perspectives or to schedule a call with one of our graph and data visualization experts. We can help guide you to the best solution.